Okay, let's try this again. So as you can tell, the computer kind of cut the video off. But luckily we had finished with example 1, part B. So let's look at example 2, parts A through E. All right, so here they're asking you to identify by the degree. So what we're going to do, we can multiply this out. So I could come right here and say 3x times x squared, and I would get 3x cubed. And I could say 3x times -4 and get negative 12x. And I could see that the degree here would be 3. So since the degree is 3, that would make that a cubic function. But another way that we could do this, I know that x squared is the biggest x right here, and then x to the first is the biggest x right there, so 1 and 2 would give us 3. So if you understand the process of distributive property, you would know that this largest degree times that largest degree would give you the largest degree in the end. And since we're only trying to identify by the degree, then that means we're only looking at the largest degree. So like right here, I can come right here and say, well, 4x squared, that's an x squared. What is the largest degree in that trinomial? Well, that would be the x to the 4th. So 4x squared times negative 5x squared would give us a negative 20x to the 6th, because remember, when you multiply like basis, you add the exponents. So here the degree would be 6. So that would make that a polynomial of 6th degree, a 6th degree polynomial. Now, could you come in here and multiply all the way out? Of course you can. You could come right here and say 4x squared times 2x cubed, and you would get 8x to the 5th. We've already multiplied this one. So then we just come right here and say 4x squared times 6, and we'd get our 24x to the 2nd. All right, for this one, again, you can multiply all the way out, but I do the shortcut method. This is the biggest degree of that binomial. This is the biggest degree of that trinomial. So when we multiply x times x squared, we'd get an x cubed. That would be our biggest degree, which that's going to make that a degree of 3. So that is going to be a cubic. Let me see, this is a 6th degree poly right here. All right, for D. All right, so take about 45 seconds and see if you can figure out what the degree of D would be without having to multiply it all the way out. All right, so let's see what you got. The biggest degree right there is 3. The biggest degree right there is a 1. And the biggest degree of that set of terms is a 1. So 3 plus 1 plus 1 would be 5. So this is actually going to be a degree of 5. And since it's a degree of 5, that would make that a quintic function. All right, and then for E. All right, so again, here's a term, here's a term, here's a term. All right here, that term has a 1, an exponent of a 1. This term, the biggest exponent, is also of 1. This term, notice, is x minus 1 squared. So when you squared it, you would end up with an x squared right here. So that is the biggest exponent right there. So we got 1 plus 1 plus 2. So that would give us a degree of 4. With a degree of 4, that would be a quartic. Now that's the shortcut method. And obviously I always work these out ahead of time. I create the problems and I work them out. If you actually worked it out, okay, so like right here, I'll use my distributive property to multiply x times all of this and 3 times all of this. Combining like terms, this is what we would end up with, our polynomial. And we would see that that's the biggest exponent of 3, so that's why it's a cubic. And for this one right here, I would multiply these two binomial factors. And then once you multiply these two right here, you'd multiply it by x cubed. And this would be your polynomial that you get. So that makes it a quintic. And this one, that x minus 1 squared means you would do x minus 1 times x minus 1, which would give you x squared minus 2x plus 1. Then x times x plus 3 would give us x squared plus 3x. So when we multiply the binomial times the trinomial, we would get this right here, which see x to the fourth is the biggest, so it would be a quartic. All right. In example 3, they're asking us to identify the leading coefficient and the degree. And so leading coefficient. All right, first of all, let's recall what a coefficient is. A coefficient is simply the number in front of the variable. All right. To make it a leading coefficient, it is the coefficient of the number with the highest degree, of the term with the highest degree. So like right here, we got a 2, 1, and 3. 2, 1, oh, not 3, but 0, sorry about that. So the 2 is the highest degree, so that means the leading coefficient is a 5, so your LC is a 5, and your degree is 2. All right, for part B, here we have a degree of 4, a degree of 2, and a degree of 0. The biggest degree is 4, so that makes the LC your negative 2, because that's the coefficient of what would be in front, which it is in front, if it was when it's in standard form. So your LC is negative 2. And your degree here is 4. All right, for C. All right, our degree for this first term is 4. Our degree for the second term is 7. Our degree for the last term is 1. So 7 is the biggest degree. So our degree here is 7. That makes the leading coefficient be a negative 2. Your LC is negative 2. Because this is not in standard form. If we put it in standard form, we would have negative 2x to the 7th plus 5x to the 4th minus 3x. So the negative 2 would be the leading coefficient. It would be the coefficient in front if it was in standard form. All right, take about 20 seconds and pick out the leading coefficient for D as well as the degree. All right, so let's see how you did. All right, here, this term has a degree of 2. 9x, the x is to the first, so it has a degree of 1. 8x cubed, that has a degree of 3. 7x to the fourth, that has a degree of 4. So your biggest degree is 4. So the leading coefficient is the coefficient in front of the x to the fourth, so that would be a 7. So this is how you find your classification by degree, your classification by the number of terms, and also your leading coefficient. Now, just as a hint, I really do like these problems right here, so I would definitely know how to pick out the degree from right here. Like I said, you can either look at the highest degree of each term and then add those degrees together, and that's how you would get this, or you can multiply it all out and see what you got. The last thing that we're going to look at today is our multiplicity. Now, some of you may have heard of multiplicity, but many of you probably have not heard of multiplicity. Okay. So multiplicity is simply the number of times a distinct root. Remember, roots are also called zeros. They're called solutions. and they're also called x-intercepts, appears in factored form. And remember, we abbreviate factor form as FF, and it's in the form of x minus your root. All right, so what we're going to do is we're going to come right here, and we're going to look at these right here. All right, so we're just going to do a sketch of the graph. So I've got x plus 1. So x plus 1. And we notice that's a straight line. Okay, so here we have a straight line going through 1. Okay, how many times is that root used? Well, it's only got 1x plus 1, so that root of negative 1 is used once. That x-intercept of negative 1 is used once. All right, for our second one, we got x plus 3 times x plus 3. Well, that root right there is negative 3. That root right there would also be a negative 3, because remember, whenever we pull it out of the equation, your h or your r in this scenario would always be the opposite. How many times is that being used? It's being used twice, but it is still one distinct root. A distinct root means that individual number. It can be used more than once, but it's still just a negative 3 being used more than once. So let's look and see what that graph would look like. All right, so coming right here, we've got x plus 3 times x plus 3. Okay. We can see that that is a parabola at an x value of negative 3. Okay. All right. Then looking right here, we've got x minus 2 times x minus 2 times x minus 2. All right, your root here would be 2. Your root for this x minus r would also be 2. All of these, notice we're in factored form, and your root for this one right here would be 2. Let's look and see what that graph would look like. X minus 2 times x minus 2 times x minus 2. All right, so we got it in 3 times. And we notice that's our squiggly. Okay. And, oops, I didn't draw it as good. A little hiccup there. Oh, it's supposed to look like this. There we go. And a little hiccup there. Oh, I'm just making it worse, aren't I? All right, so right here too. All right, so look at the different shapes here. When we use the distinct root once, it was a straight line. When we use this distinct root twice, which means distinct means the individual number, but we used it twice, it was a curve. So kind of like a bounce. It hit the floor and it bounced back up. When we use that distinct root of 2 3 times, it gave us a squiggly line. Okay. All right, this is going to be important because you're going to be required to look at a graph and determine how many roots you have. So, all right, so I'm going to come right here. X plus 3 times x plus 3. That is the same thing as x plus 3 squared. Okay, so we got that parabola. All right, if I change that square to the 4th power, Notice it's still a parabola. If I change that, oops, hit the wrong one. I want to copy that. And if I change that to the 6th power, notice it's still a parabola. If I change that to the 8th power, and you're probably starting to see that I'm only using even numbers here. Okay, that's still, let me come in here and change these colors. Right, it's still a parabola. But if you notice, looking closer right here, give it a chance to focus. The bigger the degree, the flatter it's getting right here at the vertex. Okay? So they all have the same shape. So what's the smallest exponent you can have and still have that U shape? And that would be 2. You can have a degree of 2. Okay? So when you have a minimum degree of 2, you get that parabola shape. All right, so let's come back here and just look at x minus 2 times x minus 2 times x minus 2. That is the same thing as x minus 2 raised to the 3rd. We see that squiggly. So if I come right here and do x minus 2 raised to the 5th, it's still the squiggly. I come right here and do x minus 2 raised to the 7th. It's still a squiggly. I come right here and do x minus 2 raised to the 9th. It's still a squiggly. But just like with the parabola, the higher the degree, the flatter it gets right there at the point of inflection. So what is the smallest value for the exponent you can have and still have that squiggly? Well, that would be 3. If you use the root 3 times, you get the squiggly. Okay, so you're going to be asked to identify the minimum degree. So let's look at a problem together, and then we'll let you try this one, and then we'll be done. Okay, so let's say that I had a problem that looked like this, and I asked for the minimum degree. And they call it a minimum degree because, like right here, this is a bounce. That bounce could be an exponent of 2, it could be an exponent of 4, it could be an exponent of 6, it could be an exponent of any even number, but the smallest number that we can have for an exponent and get a bounce is a 2. So right here, if you notice, this is a straight through. It goes straight through. So that's only, that root right there, that distinct root is used once. This right here is a bounce. So whenever you have a bounce, whether it's opening up or whether it's opening down, it's used at least twice. When you have a squiggly line, it is used at least 3 times. You have to use that root 3 times. Right here we have another bounce. And so let's see, this is squiggly. And this was a bounce. And so here we have another bounce. That's that used at least twice. And then this is a straight through, so that's used only once. So when they ask what is the minimum degree, let's count this up. That's 1 time, 2 times, so that's 3. That's 3 more times, so that's 6. That's 2 more times, so that's 8. And that's 1, so that's 9. So here the minimum degree would be 9. Sometimes they might ask you how many distinct roots are there. Okay, so sometimes the degree and the number of roots can be different. How many distinct roots? So how many different numbers did we use? We got 1, 2, 3, 4, 5. So there are 5 distinct roots, but some of those roots are used more than once. So that's why we have a degree of 9. All right, so take about 1 minute and tell me what the minimum degree of this last example is. All right. So here we got that squiggly, so that's used a minimum of 3 times. Here we have a bounce, that's used a minimum of twice. And here it goes straight through, so that's only used once. So 3 plus 2 is 5, plus 1 is 6. And the minimum degree here is 6. How many different roots do we have? We've got one root of -4, another root of 1, and another root of 3. So we only use 3 different roots, but some of those roots were used more than once. So you have 3 distinct roots, but a minimum degree of 6. All right, so we are finally done. So make sure you put your name and date on the notes and submit them, please.